All right, we're back. We're on page 129. We're going to keep going, and let's just see what we got here. So one important place where the dot product shows up, okay? Given vector u and vector v with all their subscripts, we're going to find the angle between the vectors. Okay, so this is actually, I'm of the opinion, it's actually kind of easy to do in 2 dimensions. And like, there's a lot of geometry that helps you out. And actually, if you paid attention, I think on the previous page, we sort of maybe worked out how to do this, sort of. But let's see if we were right. So first thing we're going to do is we're going to add to this picture, excuse me, the vector u minus v. So u minus v, so that's like u plus negative v. So if v is here, which it is, then negative v is here-ish, right? So then u plus negative v would go this way, and then we would go from here to here. But then you look at that and you're like, oh, I could pick that up and move it. So u minus v is actually this vector, and it points that way. So I'm going to add that to my picture. So like that. And then it points this way. So this is u minus v. All right, so we got u minus v. Now the angle between the vectors is going to be this angle right here. And then if you look at it, everything is basically set up to use the law of cosines. An interesting, well, a sort of interesting thing to keep in mind, when you're using the law of cosines here, you're not really using the vectors, you're using their magnitudes, right? So like a vector has magnitude and direction, a vector is a thing. We need their magnitudes to actually do this. So what I'm gonna say is that the magnitude of u minus v squared is equal, which if you remember, that's just u minus v dot u minus v. I don't know if that's going to be useful. Sometimes I can help you like work out what to write, but it doesn't really matter. The magnitude of u squared, the magnitude of v squared minus 2 magnitude of u, magnitude of v, and then cosine of theta. It's always really weird when you multiply 2 magnitudes because the notations get like really bunched up. There's kind of nothing you can do about it, but even when you type it, it does not look great. So what do I need to know? I need to know, so u minus v is going to be u1 minus v1 comma u2 minus v2. All right, so then the magnitude of that is the square root of those things, of the sum of those things squared. And then I need to square that, so it's just going to end up u1 minus v1 squared plus u2 minus v2 squared equals, let's keep going. So u1 squared plus u2 squared plus v1 squared plus v2 squared minus 2. Now, you have no reason to know this, but don't bother with these yet. Magnitude u, magnitude v, cosine theta. Just leave those as they are. Next step, what we want to do is just expand everything you can. And yeah, it's going to be a little gross. So we'll get u1 squared minus 2u1 v1 plus v1 squared plus u2 squared minus 2 u2 v2 plus v2 squared. That's the left-hand side. And then this equals everything that's on the right. So what I'm going to do, I'm actually just going to copy and paste. So while I do that, you should frantically handwrite it to try to keep up. So I get that. Is that going to fit? Or can I? Hold on. I got to rearrange. This gives you plenty of time to catch up. Got there. And then can I move it back somewhere? Perfect. Okay. So we get this. Now, what's useful or nice is that everything that's squared is actually showing up on both sides here. So that means that when I go through, I can just subtract those off from both sides and they'll just be gone, right? So if I go through, it's like boom, 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 because of there, 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 there. So really at this point, all that I have, I'm going to resist the urge to just copy and paste this, which I really want to. Negative 2 u1 v1 minus 2 u2 v2 equals, what's left over here? Negative 2, the magnitude of u, the magnitude of v, cosine of theta. All right. I mean, I feel like we should kind of obviously divide through by negative 2. So let's do that. Get u1 v1 plus u2 v2. That's amazing, or you should feel like that's amazing. Magnitude of u, magnitude of v, cosine of theta. All right. But what's u1 v1 plus u2 v2? We know this. This is just u dot v. Nice. Magnitude u. So is this what we thought before? Magnitude v, cosine of theta. We think the dot product, well, actually, we don't think it. We just showed it. We just showed that the dot product is the magnitude of, the product of the magnitudes times the cosine of the angle between them. The key thing here is that this is the angle between u and v. Okay. So did we think that before? Let's look at this one, right? Here, when we calculated our dot product, we ended up with 5 times 14, product of the magnitudes, times the cosine of 7 pi over 12. 7 pi over 12 was the angle between the vectors. We actually already used this, even though we didn't know it. It just like naturally shows up when you try to find the dot product using this like, I don't know, magnitude unit vector format or magnitude direction angle format, however you want to call it. So this is good, mag cosine. That's one of my all-time favorite students. Basically used to chant that all the time when she was trying to remember it. So it's mag cosine, dot product, mag cosine, magnitude, 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 cosine. I thought that was my pointer, but it's not. Okay, so it's in the box. Why is it in the box that way? Well, typically you solve for cosine. And why do you do that? I don't really know. I mean, you do that because you're talking about the angle between the vectors a lot, right? So now let's think about this thing, right? So the cosine of theta is the dot product divided by the product of the magnitudes. There's a couple things that we know. Magnitude of u is greater than 0. The magnitude of v is greater than 0. Therefore, u dot v divided by magnitude of u, magnitude of v, has the same sign as u dot v, right? Because the denominator can't be negative. So the dot product could be positive, negative. It could also be 0. So the sign of cosine, the SIGN of cosine, whether cosine is positive or negative, is determined by the dot product. Once you have that down, you end up saying that theta is the inverse cosine of u dot v over the magnitude of u, magnitude of v, right? So the angle between the vectors is the inverse cosine. Well, what do we know about inverse cosine? Inverse cosine comes from this half of the unit circle. And if you're doing the inverse cosine of a positive, you would end up in the first quadrant and you would get an acute angle because everything is positive there. If you're doing the inverse cosine of a negative, you end up in the second quadrant because cosine is negative in the second quadrant because only sine and cosine are positive there. So under what conditions will the angle between the vectors be acute? If you get an acute angle, that means you did the inverse cosine of a positive, which means the dot product must be positive. So if the angle is acute, then u dot v must be greater than 0. How about obtuse? It's just the opposite argument. If you get an obtuse angle, you must have done the inverse cosine of a negative. To do the inverse cosine of a negative means that you must be dealing with a second quadrant angle. So, or rather, if you're finding the inverse cosine of a negative, that means the dot product is negative. There's no way it's not. So u dot v, I don't know if I said that right. Like even after I don't know what I said originally and I don't know what I said to correct it. So whatever. If the angle is obtuse, It means it's a second quadrant angle. It means that the inverse cosine, you did the inverse cosine of a negative. The only way that can happen is if the dot product is negative. Okay, how about if the angle, if the vectors are orthogonal? If the vectors are orthogonal, then the vectors form a right angle. So this, I don't know if it actually, it's weird. I don't know if it actually says that anywhere in the notes. I mean, we've said it. So form a right angle. It's really, they form a right angle when you put their terminal point, they form a right angle when you put your initial points at the same location. Actually, I guess if you put the terminals, you would also get a right angle. It's just like, don't think that way. Always start at the beginning, right? Start at the initial points. So this one will be the case if you're doing the inverse cosine of 0, because the inverse cosine of 0 is pi over 2, which means that right angle, blah, blah, blah. Just repeating myself. There we go. This is a big deal. This is a really big deal because it's the dividing line, right? Like a pi over 2 is the dividing line between acute angles and obtuse angles. And it's going to be really important if we have an acute angle or an obtuse angle. Like, are they generally so if the angle is acute, they're sort of generally pointed in the same direction. Like, not exactly, but like, you know, the same, they're working together. If the angle is obtuse, then the two vectors are kind of pointed in opposite directions. They're fighting each other. They're not working together. And that's going to have applications in like physics and in Calc 3 when you get there. Under what conditions will the vectors be parallel? There's no reason to use the dot product for this. And this is kind of why it's here. If A is equal to K times, not dot product, so I guess I'll do this for some K element of the reals. So you should not be using the dot product for that. You already knew that. So what I'm going to do is end this video here, come back in the next one, and actually probably use this, maybe, I don't know. I guess we will find out together. So I will see you there.